So type 1 and type 2 diabetes both reflect the relevance of insulin in understanding the Randle cycle. The relevance of insulin and the Randle cycle in altering hunger. This is particularly relevant in the type 2 diabetic. So I'm deliberately placing it here as we wrap up after talking about insulin resistance in the type 2 diabetic. The brain is unique. It doesn't quite fit into our understanding of the Randle cycle because it doesn't use fats for fuel. In general, even though it has access to fats, it's, I think, more correct to say that the brain uses fats for structure. It uses it to build stuff rather than using fats to burn for energy. So the brain's fuel choices are between glucose, which is a ubiquitous fuel source, and ketones. That's the brain's availability. And once again, the Randle cycle would be relevant here. A brain cell, like every cell of the body, just can't infinitely use all energy sources available to it. It doesn't need an infinite or an unlimited access to energy. It's going to choose one or the other. And I wanted to mention this in the context of hunger, because if you have insulin resistance, the brain can become insulin resistant. That there are regions of the hypothalamus that can become insulin resistant, where particularly we have our hunger and satiety centers. As that part of the brain becomes insulin resistant, it can't pull in glucose as well. Even though there's plenty of glucose in the blood, the brain isn't getting it in very well because the glucose isn't working well. So the glucose doors aren't opening very well. GLUT4 isn't working particularly well. Now imagine in that same situation, because of the high insulin, reflective of their insulin resistance, what has happened to the ability of the liver to make ketones, which is a favored fuel by the brain, or of the brain. Of course, it's compromised. And so it's this particular metabolic tragedy where the brain, which has so much glucose surrounding it, isn't able to use it very well because of the insulin resistance. And the one fuel that it's crying out for, namely ketones, in the midst of this compromised glucose use, is a fuel that it doesn't have access to. It's not available, to be a little more precise, because of the high insulin inhibiting the liver's ability to burn fat. Because insulin is stopping the liver's fat burning, there is a compromised production of ketones, resulting in the brain going a little hungry. And if the brain is going hungry, not only can that contribute to chronic neurological pathologies like depression and migraines and Alzheimer's disease and Parkinson's, all of those have this aspect of glucose hypometabolism to it. In other words, a compromised ability to use glucose. But to compound the problem, we're not giving it access to the alternate fuel source, namely ketones. So I like to sort of jokingly invoke the rhyme of the ancient mariner here, which may sound a little familiar. The sailor who's on the sea, tossed and dying of dehydration, bemoans the fact that he's surrounded by water everywhere, nor any drop to drink. He can't drink it, even though he's surrounded by water. That's sort of analogous to the brain being surrounded by glucose, but it can't get it. And the one thing it's crying out for, the fresh water that we could provide this stranded sailor, would be the ketones in the case of the brain, to bring the analogy back full circle. So there's a relevance there, not only to the brain going hungry and contributing to pathologies, but if the brain is hungry, it thinks the body is hungry, and then it stimulates hunger. That's this idea of the fuel partitioning theory of obesity that I'm going to talk about in a future lecture. So stay tuned. And of course, insulin being extraordinarily relevant.